Hi guys, it's Mrs. Allison. Today we are going to look at our final rules of exponents, our number 5. And since this doesn't have all of them filled out for you, like we've been doing the last couple days, I just want to go through those first 4 rules just as a reminder. Okay, so remember our first rule of exponent was our 0 exponent rule. And remember with 0 exponents, the definition says it's a to the 0 equals 1 for all a that are not equal to 0. So as long as it's not 0 to the 0, the result is 1. Our next rule was our negative exponents, and I think this one is the weirdest one. And remember that said that if we had any a to a negative n power, we would flip it, or it would become the reciprocal and become a positive power. Or this could start down low. If we have 1 over a to the negative n, the reciprocal of 1 over a is just a, and it would be to the positive n. And then we looked at our product rule. Remember, product is the answer to product is the answer to a multiplication problem. So if we had a to the n times a to the m, where the bases are the same, then we add their exponents. Then we have the quotient rule. And the quotient rule says that if we have any of the same base divided, so a to the n over a to the m, that we are going to subtract the exponents, top minus bottom. And then if the answer ends up negative, we would need to then use that negative exponent rule to move it down. Well, the final rule that we're going to talk about, the last one for this properties of exponents, is what we call a power to a power. Power to a power rule. Okay? And the power to a power rule looks like this in its mathematical definition. A to the n raised to the m. So you can see what we're talking about. You have an exponent right here, a to the n, you have that power, and then it's raised to another power. And the result of this is a to the n times m. A to the n times m. Okay, well, what does that mean? Like, if we talk about this rule in more of a layman's terms, more in something that's a little bit easier to understand, we would say we are going to distribute the outside exponent to both the coefficient and each variable. Then what we're going to do is to multiply the exponents, and the base stays the same. Meaning it doesn't change the value of the base, it only changes the value of the exponents. Okay, so what does that look like? Well, I want to look at this first example several different ways. So if we go purely by definition, and let me rewrite that mathematical definition here, it says that if we have a to the n raised to the m, it equals a to the n times m. So we distribute the outside exponent to the coefficient and each variable, and then multiply the exponents. Okay, well, in this problem, there really is only a coefficient that happens to have an exponent as well. So we are going to multiply those two exponents. So this would be 7 to the 2 times 3, using just the mathematical definition, or 7 to the 6th power. And if you were to type each of these into your calculator, 7 to the 2nd cubed or 7 to the 6th, we would get the same answer either way. Now, when we look at this just another way, let's do it in a different color. Let's do it in green. 7 squared cubed. To be cubed means we're going to do that thing 3 times. Do you agree that that says the same thing? And what we know is that doing this, we can use the product rule that we used yesterday. The bases are all the same, so I can add their exponents. So I get 7 to the 2 plus 2 plus 2, or 7 to the 6th. Or I can even take this a step further. We know that 7 squared to the 3rd means 7 squared times 7 squared times 7 squared. And to be squared means to do it by itself. So 7 times 7, 7 times 7, 7 times 7. How many 7s do we have? We have 7 to the 6th power. So you can see why it benefits us maybe to know that rule, is it allows us to just do the problem a little bit simpler. Okay, well, that was just one. Now let's step it up just a notch to see what it looks like when we do this with a little bit crazier numbers, like 3x to the 9th squared. So I'm going to take this outside exponent and I'm going to distribute it to the coefficient because it doesn't already have an exponent. And I'm going to distribute it to the exponent x to the 9th. So what that looks like is 3 squared x to the 9th squared. Now I may or may not actually take this step, but if I keep going with this, 3 squared we know to be 9, and x to the 9th squared, I have a power to a power and I multiply, so I would get x to the 9 times 2, or 9x to the 18th. Well, if we wanted to look at this a different way, just to check to make sure we did our work correctly, 3x to the 9th squared means that we're going to multiply 3x to the 9th times 3x to the 9th. And I know using my product rule, I would multiply normal numbers by normal numbers, and then x to the 9th times x to the 9th to get x to the 18th when I add those exponents together. So we get the same thing either way. All right, I'm going to try this next one, just because it looks a little bit different. And then you are going to try one. Okay, here we have d to the 5th over w to the 4th squared. So I'm going to take that squared and I'm going to distribute it to each of my variables. So really what I have, if I were to take this step to write it, is d to the 5th squared over w to the 4th squared. And d to the 5th squared is d to the 10th over w to the 8th. And since these bases are not the same, w and d are not the same, this is as simplified as this problem can get. All right, let's see what you can do. Let's put all of these steps together, hit pause, and try this next example just to see how you do, and then we'll go over it together. All right, let's see how you did. I know this squared needs to distribute to the 6, the coefficient, the x squared, and the y cubed. And to the 4 and the x cubed. So this is what it looks like when we distribute that exponent to all of the things in the parenthesis. Now what I'm going to do is I'm going to simplify these. 6 squared, 36. X squared squared would be x to the 4th. We multiply. Y cubed squared would be y to the 6th. We multiply. Over 16x to the 6th. If you got that far, you did great. Now, there are a couple more steps because this now created a problem that has a quotient rule in it. See how we're combining all the different types of rules? Remember, when we deal with a quotient rule, we need to simplify normal numbers and we need to simplify variables with like bases. Since the y doesn't have another y with it, we're not going to simplify that. Well, if I reduce my fraction 36 over 16, I know that 4 goes into both of those. 4 goes into 36 9 times, and 4 goes into 16 4 times. Then with the x's, remember we subtract top minus bottom, or we can use the shortcut that we talked about. This would be x to the negative 2. Darn, then we create a negative exponent, but that's okay. We know what to do with that. Over y to the 6th. Now remember, negative exponents we can't leave in the numerator. So rewriting this, I'm going to get 9 over 4. The y to the 6th can stay in the numerator, but the x to the negative 2 needs to move to the denominator and become positive. So the final answer for this problem is 9y to the 6th over 4x squared. All right, you ready for some real fun? I would love for you to hit pause and just try this crazy looking problem. When attempting a problem like this one, I can tell you how I will approach it. That does not mean it is the only way to do it. What I'm going to do is I'm going to simplify any big outside exponents. And what I mean by the big outside exponents are the ones that need to be distributed in, the ones that use the power to a power rule. So I'm going to start there. In doing that, I would get 16 x to the 3rd, y to the 3rd over 4x. Notice I'm doing no other simplifying. Times 8x to the 5th, y squared over, here we'd get 2 squared, y to the 10th. We have to square that too because remember it needs to distribute to the coefficients. Now, at this point, you have several choices. You have the choice to reduce each fraction independently, then multiply straight across, but then you may have to reduce again. So what I like to do is multiply straight across first. Meaning I'm going to do 16 times 8. And we know 16 times 8 is 128. Then I have x to the 3rd and x to the 5th. Let's highlight this in a color. X to the 3rd, x to the 5th. They're multiplying, so I'm going to add their exponents. And the y to the 3rd and y squared would leave me with y to the 5th. Over. Then I'm going to do the normal numbers down here. I have 4 times 4 because 2 squared is 4. So 4 times 4 is 16. I don't have any other x's and I don't have any other y's. So this is going to be xy to the 10th. Now you guys, this becomes a quotient rule. And it becomes a quotient rule that I'm going to simplify by doing the normal numbers first. And 128 divided by 16, 16 actually goes into 128 evenly. We know it goes in 8 times. So I'd have 8 over 1. The x's are division, so I'm going to subtract them. And the y's are also division, and so I'm going to subtract those. What color should I do those in? Let's do them in black. So we'd get y to the 5 minus 10. So what we have right now is 8 over 1 x to the 7th y to the negative 5th. Darn it, here's another problem. I can't have a negative 5th in the top, in the numerator. So I'm going to move that to the bottom. The denominator was looking lonely anyway, so we would get 8x to the 7th over y to the 5th. This is as simplified as I can make it. I don't have any other x's in the numerator and denominator to simplify them with. This is as much as I can do. Now that's kind of a crazy problem. I really want to make sure that you feel good with some of the other problems we worked on today. So if you need to, go back and watch this video again. Make sure you ask questions of me as they come up. All right, you guys, check on your homework and have a great day.